Now, not by dissociation of calcium carbonate in aqueous solution, as we've looked at many times previously, but instead by imagining the possibility of a chunk of calcium carbonate in the open atmosphere, for example, of our classroom, decomposing by this process. Now, to get at the data for this analysis, we go back to Table 1 at the end of Chapter 20, Thermodynamic Properties Data Table, and look up the standard enthalpies of formation for each of these system components and the standard entropy for each of these system components. From that, we get this change in standard enthalpy for this reaction system, change in standard entropy for this reaction system, and at 298 K, essentially the temperature in the room, we get this delta G0 value. Well, the delta G0 value is large and positive. So it tells us if we were to assemble these system components, would a change take place? You betcha. But what would the change be? This way. Go back to reformation of calcium carbonate. But if instead we consider a system which initially, for these components, has got calcium carbonate only and no calcium oxide and no CO2, would something happen? Yep. Then this thing is going to go spontaneously until equilibrium is established. Now, the chemical form of the equilibrium constant for this reaction is simply the partial pressure of CO2 gas. So if we want to know how far this reaction goes, then we've got to get a handle on partial pressure of CO2 gas. So we take our delta G0 value and with this relationship calculate log K and K. Now when you do this, when you calculate an equilibrium constant from thermodynamic data, you will get a unitless quantity. Because rigorously speaking, thermodynamic equilibrium constants are unitless quantities. But from a practical standpoint, as for example analyzing this system, where we know the equilibrium constant is expressed in terms of partial pressure of CO2, if we want to do some calculations on this system to find out what the partial pressure of CO2 is at equilibrium at 298 K or at some other temperature, and then use that in order to find out how much CO2 that is, we've got to attach units to this equilibrium constant. What units do we attach? Well, thermodynamic folks, for gas pressures, today use bar. But the data that I have given you is probably still corresponding to pressure in atmospheres. But again, there's not much difference because magnitude-wise, 1 atmosphere is 1.01 bar. So they're about the same. So we're going to take this equilibrium constant and attach to it the unit atmospheres. And remind you again, if you calculate an equilibrium constant from thermodynamic data, which is what we did here, here's the thermodynamic data that we used, and you want to do some analysis of the reaction system for which you've calculated K. You want to find out about pressures, or you want to find out about mole quantities, or if you're dealing with a system that contains solute species, you want to find out about concentrations. You're going to have to attach units to this K. Where do we get the units? Since the calculation doesn't give us any units. We get the units by looking at the equation for the reaction. Just like we did in chapter 17, and again in chapter 18, and again in chapter 19. From any equilibrium reaction, we know the units on K. So, if I want to consider the same reaction system, but with different multipliers, what's the K value for this system? What's the K value for this system relative to this K value? Will the K value for this system be larger than this K value or smaller than this K value? And what will the units be? What if I look at the same system but use the multipliers 2 throughout? Now what's the K value relative to this K value? What's the unit or units for the system considered with this multiplier of 2? Again, the reaction equation answers the question. Tell me, with this number for K, how would you get this K? What would you do? Take the square root. So, would you get a number that's bigger or smaller than this? Bigger? Because this number is smaller than 1. And what would the units be? What would it be? What would the units be? We could take the square root of units as well. It's atmospheres to the 1/2. Here, square this. Now, if you were going to do system analysis, and you had this reaction expressed with these coefficients or with these coefficients, would you be able to operate with atmospheres to the 1/2? Would you be able to operate with atmosphere squared? You recognize that if you used these coefficients for this reaction system and got this value for K, you'd have to square this to get at pressure. Because pressure is atmospheres, not square root of atmospheres. If you use this series of multipliers, now you'd have to take a square root. You'd wind up with this system at the end. Now, significance of K. There's the K value. 2.3 times 10 to minus 23. What's that mean? Draw a picture. To get a handle on this quantitatively, let's imagine that we have available a 10.0 liter volume flask and we free it from CO2. I don't care if there's oxygen in there or nitrogen in there, but no CO2. And we put some calcium carbonate in there at 298 K. Tell me, under these conditions, would the calcium carbonate decompose spontaneously? Yep. Would decompose spontaneously until the partial pressure of CO2 was 2.3 times 10 to minus 23 atmospheres. Tell me, if along with the calcium carbonate, we also put some calcium oxide, would that prevent the calcium carbonate from decomposing? Yes or no? Yes, no. No. No CO2 in there. So back to this significance of K. Regarding our imagined system of calcium carbonate in a 10.0 liter flask which has got an atmosphere that's free of CO2. How many moles of CO2 will we generate by this reaction going spontaneously till we get a partial pressure of 2.3 times 10 to minus 23 atmospheres at 298 K? Well, CO2 is a gas whose behavior is describable by PV equals nRT. Does that seem to be a fair statement to you? On what basis would you argue that CO2's behavior is reasonably well described by PV equals nRT? You think 298 K is a temperature well above a temperature at which CO2 will condense? What would you do to find out if you didn't know? Would you get out a properties table and look up CO2 and see what temperature at which it began to condense? Any of you know straight off what the temperature is generated by this stuff called dry ice? You know what dry ice is? What's dry ice? It's just a common name for solid CO2. Dry ice. No liquid. I once observed a student who had the misfortune of working in a research laboratory with some, shall we say, perhaps somewhat less than friendly graduate students. The undergraduate student was doing an experiment, and it said, charge the condenser with dry ice. So the poor undergraduate student had gone to the ice bin, water ice, brought the ice back to the condenser, and with large gobs of paper towels, drying these ice cubes. I'm going to put them in the condenser, but in Florida, where the temperature is considerably above 0 centigrade, no matter how feverishly the student dried the surface of the ice, liquid would form. I can't get this ice to dry. And then another graduate student from a different research group saw what was going on and told the poor unfortunate undergraduate that you're supposed to be using solid CO2, not solid water. At which point, the poor unfortunate undergraduate charged out of the laboratory and, to my knowledge, never returned. So I guess there is an upshot to this, which maybe led to the graduate students whose responsibility it was to run this reaction maybe not being quite so happy because now they had to do it. In any case, from this arithmetic, we get 9.4 times 10 to minus 24 moles. And if we multiply that by Avogadro's number, which gives us a handle on molecules per mole, which you all know about, we get 5.7 molecules. A result of the result of which, this result I put quotes on it. 5.7 molecules. Why? Is this an impossible value? Molecules are entities, like chairs. Can I chop up a chair? Yeah, but after I chop up a chair, I don't have a chair anymore, I have junk. It's like CO2. If I break any of the carbon-oxygen bonds, I don't have CO2 anymore. So we'll rewrite this as 6 and take away the quotes. 6 molecules only of CO2 molecules. 6 molecules only of CO2 will wind up being present in this flask, volume 10.0 liters, at a temperature of 298 K, produced by the spontaneous decomposition of calcium carbonate, regardless of how much calcium oxide was also in the flask. And at that point, equilibrium is established, and the spontaneous decomposition would shut down. Well, that tells us why our calcium carbonate, if we allow it to stand here on the lecture bench for as long as we so choose, and I or no one else writes with this calcium carbonate, the amount of calcium carbonate here is not going to change. Why is that true? You think there's some CO2 in this atmosphere? Now there's a hell of a lot more CO2 in the atmosphere. Because it's a byproduct of our breathing process. But it is true that calcium oxide, the solid product of this reaction, is a very important industrial material. And it's also true that in the geological surface of Florida, there's a lot of calcium carbonate. You shouldn't be too surprised at that, since calcium carbonate is the principal component in crustacean shells, common everyday seashells. So there's a lot of calcium carbonate to be found in Florida, particularly near the beaches. And by getting calcium carbonate to decompose, we can make calcium oxide. That's the solid product of this reaction. And last I checked, which I will admit is a long time ago, calcium oxide is, or was at that time, and probably still is, listed among the top 10 chemical materials produced in terms of tons per year in the United States. Calcium oxide's got a lot of uses. Well, how can we make calcium oxide by this process? Well, we're not going to achieve it at 298 K. But if we go back and look at our thermodynamic data, we know that change in enthalpy, standard change in enthalpy, is standing strongly against this reaction taking place. But the standard change in enthalpy says if it ran the show, this thing is going to go. Because this reaction proceeds with a favorable change in entropy, which shouldn't be surprising to you because it shows 1 mole solid become a mole of solid plus a mole of gas. And entropy gases is in and of itself gives us reason to recognize why this reaction should go if entropy runs the show. So what are we going to do to make entropy run the show? What can we control regarding conduct of this reaction? Temperature. Let's heat it up. Make the T delta S factor ever larger. So we've written this here. How can we make calcium carbonate decompose spontaneously at standard state conditions? Remember what standard state conditions means? For this system? What's that mean? Means we got calcium carbonate present. Means we got calcium oxide present. Because by definition, pure solids are in the standard state. But if CO2 is present under standard state conditions, what do we know about CO2? What do we know? It's present at a partial pressure of how much? What? How much? 1 atmosphere or 1 bar. Remember? Solutes, 1 molar or 1 molal. Gases, partial pressure 1 atmosphere. Well, this reaction will go spontaneously to give us a partial pressure of CO2 of 2.3 times 10 to the minus 23 atmospheres if we run a reaction under conditions that we've already described. But to get this reaction to go spontaneously at standard state conditions, where partial pressure of CO2 is 1.00 atmospheres, we recognize from our relationship delta G0 is minus 2.3 RT log K. If the magnitude of K is 1, and the log of 1 is how much? You know this. Log of 1 is 0. Then delta G0 at a partial pressure of CO2 of 1 atmosphere for this reaction system, delta G0 is equal to 0. We wrote that down. And if delta G0 is equal to 0, then delta H0 is equal to T delta S0. So with that, we can calculate the temperature for this decomposition to take place under standard state conditions. So I did that here. And in passing, I'll remind you that we're treating delta H0 and delta S0 as isothermal reaction system properties. That's not entirely true, but it's close enough. Not entirely true because heat capacities of materials do change somewhat as you subject the material in question to change in temperature. But you'll pay attention to that in physical chemistry class if you get there. We don't need to pay attention to that now. So I get a temperature of 1091 K. For this K, this reaction system will proceed spontaneously until the partial pressure of CO2 is 1.00 atmospheres. So what I'm going to do, if I want to make the calcium oxide, is to heat the calcium carbonate in an open atmosphere, not a closed atmosphere, like this room. And I'll make sure the doors are open and the windows are open. So as we make CO2 and develop a pressure of CO2, partial pressure of CO2 of 1 atmosphere, if atmospheric pressure is 1 atmosphere, the CO2, as I produce it at a temperature above 1091 K, will have a partial pressure that's somewhat greater than 1 atmosphere. And it'll push the atmosphere back. And as long as I don't close the system, and atmospheric pressure is 1 atmosphere, or at least less than the partial pressure of CO2 produced by our decomposition reaction, this reaction will keep on going. Keep the temperature above 1091 K. And that's the way calcium oxide is made, commercially. That's question 32. Now a couple of other questions regarding this system. I should hope that from what we've just done, you'd recognize that if I want to do an investigation in a closed atmosphere, like my 10-liter flask, and the investigation which I need to conduct has got to be in a CO2-free atmosphere. Based on what we've done, how would you free the atmosphere of CO2? Chemists, for example, often conduct reactions in gadgets called dry boxes or inert atmosphere chambers, which is a fancy name for a dry box. You ever walk past research laboratories where you see this box has got a glass window And it'll have gizmos on the side which will allow you to go inside the box and put in balances or whatever gadgets you need for the system you're going to investigate. And it's got rubber gloves. You can stick your arms in there. Arms are in the rubber gloves and you work inside this controlled atmosphere. That's your dry box. Well, if you put some calcium oxide in there on an open tray, do you think that'll scavenge the CO2? Think the calcium oxide would absorb the CO2? You're daggone right. I mean, calcium oxide plus CO2 at 298 K becoming calcium carbonate has 1 over that 2.3 times 10 to minus 3 value, 2.3 times 10 to minus 23 value as an equilibrium constant. That's a hell of a big equilibrium constant. Now, a brief peek at the reaction of calcium metal, calcium element, combining with oxygen to make calcium oxide. This reaction has a delta G zero value, which is large and minus, spontaneous, at standard state conditions. Now, do you recognize from this reaction, if I tell you that delta G zero is large and minus, which means spont at standard state conditions, that it's got to be delta H zero, which is driving this reaction, because delta S zero can't stand this reaction. Does that make sense? You see, this system is, from the fundamental thermodynamic components of the system, delta H zero and delta S zero, it's kind of the opposite of this. There we've got a solid becoming a mole of a different solid plus a mole of gas. Here we're looking at a solid getting together with gas to become a mole of solid. Well, then we shouldn't be surprised to find out that this reaction is very exothermic. Now, to get a better handle on this very exothermic reaction, let's look at these S0 values, which is called to your attention by question 35 for calcium oxide versus calcium solid itself. We've reminded ourselves that standard entropies depend on formula mass, temperature, structure, phase. Well, they're both solids. And clearly this has the higher formula mass. But interestingly enough, this stuff which has the higher formula mass, for this comparison, this stuff has got a lower entropy. That relates to why delta H0 for this reaction is very exo. This is a reaction which corresponds to significant bond improvement. If you had some calcium oxide and were able to observe its properties by examination, you'd find out that it's quite crystalline, ionic. Do you think the ionic lattice for calcium oxide would be a strong lattice? What properties, what physical properties would you try to find out for calcium oxide to convince yourself that the calcium oxide lattice is a strong lattice?
Melting point.
Melting point. Melting point for this stuff is damn high. I think I wrote it down here. I don't know. Let me take a look. $2580 centigrade. Melting point of calcium solid is 842 centigrade. But 2580 for this stuff. Well, that's suggesting this lattice is a heck of a lot stronger than the lattice for calcium solid itself. In fact, calcium solid, even though it's got a rather high melting point, is a soft metal. You could take some calcium metal, and you could cut it with a butter knife. You're not going to cut any calcium oxide with a butter knife. Do you recognize that the ion-ion attractions in the calcium oxide lattice are expectedly strong? +2 calcium ions surrounded by -2 oxide ions and vice versa. You got a 1-to-1 ratio of positive to negative ions. The ions are monatomic. So you wind up with a lattice structure that's pretty daggone stable. But in calcium lattice, you've got metal-metal bonds which are not nearly as strong as ion-ion bonds. Again, the physical properties shown by calcium metal versus calcium oxide are telling you that. So that accounts for why, even though calcium oxide's got a much larger formula mass than calcium solid, why the entropy of calcium oxide is lower than that for calcium solid. Because this lattice is very rigid. This lattice is soft, bendable. Do you see a comparison of these S0 properties to diamond and graphite, which we talked about previously? Same idea. Now, let's go on with another analysis. An analysis of a system I expect you're familiar with. Well, let's talk about a couple of related questions also of a thermodynamic nature before we go on with this additional analysis. Question 36, I'll remind you, is a question which directly parallels what we've just done here. So I'll tell you to do question 36. Open the notes, if you will, and you'll see question 36 corresponds to the decomposition of aluminum sulfate. Where per mole of aluminum sulfate decomposed, you get 3 moles of SO3 gas. Now, as it should follow from what we've done with the calcium carbonate decomposition, in calculating K for this decomposition reaction, where the decomposition products are aluminum oxide and SO3 gas, sulfur trioxide. What's the equilibrium constant for this? The chemical version of the equilibrium constant. What is it for this thing?
Cubed.
Partial pressure of sulfur trioxide cubed. So when you calculate K from thermodynamic data from table 1 for this decomposition reaction, you get units-wise atmospheres cubed. So bear in mind to do question 36, you're going to have to take the cube root of this to do some practical analysis of the system. Now, question 37. We really already talked about question 37. Question 37 is asking you to consider this transformation compared to this reaction. The reaction that occurs when you start getting water molecules to decompose themselves. We've already mentioned I hope you remember this, that for a covalent bond between unlike atoms, how many ways can you break this bond? 3 ways. In this case, we've considered breaking this bond homolytically. That means take this shared pair of electrons and tear it apart such that the products of this decomposition, of this bond breaking process, will be a hydrogen atom and an OH group. These were the electrons previously partnered up to form this bond. When we reviewed chapter 20, we recognized that this thing is spontaneous at T greater than 100 centigrade with P water vapor. At standard pressure, 1 atmosphere, standard state pressure. But this thing, if you recall such, this thing is not spontaneous under standard state conditions. Until temperatures greater than 4,300 centigrade. What's the main purpose of this comparison? Main purpose is to remind us about how covalent bonds compare strength-wise to hydrogen bonds. This dashed line simulates an H bond between these 2 water molecules. Now, we reminded ourselves a covalent bond between unlike atoms can be fractured in 3 different ways. We just considered the homolytic fracture and recognized from this consideration what we just said, covalent bond, hell of a lot stronger than these intermolecular attraction forces, even though hydrogen bonds are the strongest type of intermolecular attraction forces. So rather than breaking this bond homolytically, let's consider breaking it heterolytically. Breaking it in a fashion in which both the electrons, which constitute the bond, leave with this bond breaking process with the hydrogen atom and become H minus. Or in this fashion, which converts the oxygen atom to oxide ion. What do you think is more likely? If we break this bond this way, we're going to make O plus and H minus. But if we break the bond this way, then we make O double minus and H plus. Oop. What do you think is more likely? Of course, we're talking about tearing apart a whole water molecule here. So it'd be 2 H pluses, and here it'd be 2 H minuses. Why O double minus and H plus rather than this? We know the oxygen electronegativity far exceeds that of hydrogen. So this is likely. This is not.
How is it O2 minus? How is it O2 minus?
Well, I'm talking about tearing up an entire water molecule. Okay? So all the electrons from this bond as well as all the electrons from this bond jump into the oxygen valence electron environment. So it'll make me O double minus. Now, well, this would actually make O double plus. Better get my charges right. Pardon me. In any case, we recognize from electronegativities that if the water molecule decomposes with heterolytic bond fracture, this is what we're going to get. Question: if the temperature for this is something above 4,300 centigrade, how do you think the temperature for this compares? Or let's ask the question a different way. By heating water molecules to temperatures in excess of 4,300 centigrade, we can get this to go under standard state conditions. If we heat this strongly, if we heat water molecule strongly, do you think we have a chance to make H plus ions and oxide ions in the gas phase more readily or less readily than this reaction where the products are produced by homolytic bond rupture, hydrogen atoms, hydroxyl radicals? Which do you think is more likely? That or this by strong heating? Very strong heating. What do you think? This is question 38. Think about that while I clean this slate. Think we got a chance to get this one to go? This one versus this one, given that we've already reminded ourselves that this one becomes spontaneous at standard state conditions at temperatures above 4,300 centigrade. Think we can get this one to go maybe along with this, or maybe even a lower temperature? Think we can get this one to go? What do you think? Well, let's have a vote. We didn't vote for a while. How many think we got a chance to get this one to go as well? How many think, I don't give a damn what temperature we jack the system up to, we're not going to get this thing to go. We'll only get that. We're never going to get this one to go. I think we got a half a vote there. Heavy hand. We had 3 or 4 folks who said we get this one, and we got a half a vote saying we're never going to get this one. Well, I'm going to put in another half a vote for this never going. Why not? Why not? Yet, we get a very similar reaction to take place in water solution. A reaction you've already seen many times now. Liquid phase, vapor phase. You think that might contain the answer why this can go liquid phase at room temperature? Doesn't go very far. We know this doesn't go very far. We'll just write down, consider KW. But this one isn't going to go at all. Why not? Why do you think it's possible in the liquid phase to run reactions which in many cases produce ions, but in the gas phase you're not going to run chemical reactions which produce ions? I mean, you can take atoms and put them in an ionization chamber and knock electrons away from them or force electrons onto them. But you're not going to run a reaction where you get a material like water to decompose into plus as well as minus ions. Why not? You think about this, Coulomb. The difference lies in the fact that in the liquid state, you'll have water molecules all over the place surrounding this thing. You think water molecules have a tendency to stick to something that's plus? Water molecules have a tendency to stick to something that's minus? Hey, you know that. Positive ions, stick to water molecules by attracting non-bonding electron density on the oxygen atom. Negative ions stick to water molecules by being attracted to the partially positive hydrogen atom ends of the polar water molecule, because the hydrogen atom ends are rather positive. They stick to this. So with all these water molecules surrounding the hydronium ions and all these water molecules surrounding the hydroxide ions, you insulate these things from each other. And we talked about an effect that's rather comparable. Remember the salt effect? Same idea. But when we considered the possibility in the vapor phase of decomposing molecules to make ions, there's no insulation. You can't stabilize these things in the vapor phase. It's certainly not relative to these uncharged particles, because electrically these have no attraction for each other. Chemically they do, but electrically they don't. These have a very strong attraction for each other, both chemically and electrically. Therein lies the difference. Now let's go to our remaining analysis, the one which I was making mention of before we talked about these questions. The remaining analysis which we've already talked about earlier on in chapter 21, where we talked about a piston cylinder gadget which we shall imagine to contain at normal laboratory conditions 2 moles of NO2 gas, and next to it another piston cylinder gadget where at normal laboratory conditions we imagine to contain 1 mole of N2O4 gas. And we ask the question, what happens if we let these 2 piston cylinder gadgets stand for a very long period of time so we don't have any kinetic barrier to the outcome of this thermodynamic investigation? And we said, guess what? Didn't make any difference what you started with. You're always going to wind up with the NO2, N2O4 equilibrium system. And then we took a look at that reaction, or each of those reactions, from a G-state graph. And recognize that the reason why you always get to the equilibrium system based on the G-state graph is the G-state for the equilibrium system is the lowest possible G-state for the system, which means that the equilibrium system is the most stable thermodynamic state in which the system can exist. And if you recall the G-state graph, we found out that if we were to do the experiment with the N2O4, about 20% of the N2O4 would decompose at 298 K till we got the equilibrium. On the other hand, if we started with 2 moles of NO2, about 80% of the NO2 molecules would get together to become N2O4, and then we'd be at equilibrium. Let's see if we can analyze this system quantitatively to corroborate this G-state analysis. So here's the system. Question 39. Now, question 39, as it is stated in the notes, is this system but written in the opposite direction. So if for practice, after we do this analysis, you want to do question 39 as it's stated in the notes, you'll do this analysis except in the opposite direction. Moles, NO2 gas. If we anticipate ideal behavior, we get a system volume of about 50 liters with this at a pressure equal to 1.00 atmospheres. Total pressure. P total equals P external equals P atmospheric. All the same thing. And we're at 25 centigrade, 298 K. I repeat, we now want to subject this system to thermodynamic analysis like we've analyzed our calcium carbonate decomposition, for example, to see if we can corroborate that G-state graph. And we calculate the equilibrium composition of this system based on fundamental thermodynamic data. Yep, we sure can. Now, I wrote about 50 liters. It's actually 48.9 liters, but you can do that arithmetic yourself. Here's what we need. The standard free energy of formation for NO2 gas at 298 K. And the standard free energy of formation for N2O4 gas at 298 K. We'll just take the data straight from Table 1. You know about Table 1. Plus 51.3 kilojoules per mole for NO2, and plus 97.9 kilojoules per mole for N2O4. You recognize why delta G sub F super 0 for a mole of N2O4 is not exactly twice delta G sub F super 0 for a mole of NO2 gas? Just like this reaction tells us, this stuff is made by 2 moles of this getting together to make a mole of this. So, in the event that you would imagine that the standard free energy formation of N2O4 gas is twice the standard free energy of formation of NO2 gas, because this reaction is showing the combination of 2 moles of NO2 gas to become a mole of N2O4 gas, why not twice? Why isn't this twice this? This kind of stuff I'll ask you about on the next exam. Because what I want to find out is if you understand what this thermodynamic information means. Mechanically plugging numbers into applications of Hess's law, you don't need to do that. What's the difference?
Because NO2 is entropically favored?
Sure, NO2 is entropically favored. But the driving force for this reaction is what? Delta H0. So when you factor in the delta H0 part, the bond-making part, with the fact that a mole of this has less entropy than 2 moles of this, you can recognize why the delta G0 sub F value for this can't be twice that. Close, but not twice. Now, if I double this, I get a number that's bigger than this. As opposed to doubling, this number is smaller than double this, as opposed to this number being larger than double this. Does that tell you that the bond-making part is more important than the entropy part? Does that tell you that the bond-making part is more important than the entropy part? Because you know the entropy part is for this, and the bond-making part is for this. You following me? This number is smaller than twice this number because of the bond-making part. Think about it. Let's ask another question while we're looking at this information. If you look in Table 1, we mentioned this before, let's mention it again. At delta G sub F super 0, data for all the stuffs listed in Table 1. Just about every value is minus. That means just about every substance listed in Table 1, every compound, pardon me, will form in an energetically favorable fashion from the required mole quantities of the most stable allotropic versions of the component elements. Remember, that's what the sub F means? Form a mole from elements with the most stable allotrope of the elements being considered, with the exception of phosphorus. I'm not going to bother with phosphorus now. But these delta G sub F super 0 values are large numbers but plus. That tells you, if, for example, in making a mole of this, from the elements, this number corresponds to this reaction at 298 K. And that number is large and plus, not minus. notice also that this reaction has got 1.5 moles of vapor becoming 1 mole of vapor. That tends to suggest that this is a bond improvement process, because you're going from more moles to fewer moles, right? 1.5 moles becoming 1 mole. But this says, because you know entropy's again this. Change in entropy is again this reaction. Guess what? Change in enthalpy is also again this reaction. Is that surprising? This delta G value tells us that. The reaction tells us this is going to go with an unfavorable change in entropy. Well, maybe I should say, do you expect, because this goes with an unfavorable change in entropy, that that's what's responsible for this delta G value being so large and plus? Maybe I should ask it that way. But the other side of the coin is, since this converts 1.5 moles to 1 mole, all in the same phase, you might expect this to be a favorable process from a delta H standpoint, a bond improvement process. It isn't. Delta H0 for this thing is a large number, and plus both the thermodynamic properties that we've cited, delta H0, delta S0, both not favorable for this thing. Why? Why is delta H0 endo? Bond disimprovement. What do you know about N2? What do you know about bond strengths for N2?
Very strong.
How do you know it's very strong? Why?
They're really short.
Why short?
It's a triple bond.
It's a triple bond. Yeah, you learned how to write Lewis structures. If you write Lewis structures for these things, double bond, triple bond, resonance stabilized. But that's like part of a double bond. Here, double bond, here, triple bond. That's why delta H0 is endo for this thing. As we will find later on, not right now. It is triple bond in N2. In the world of chemistry, this is the third strongest bond known. The second strongest bond known connects the carbon and oxygen molecule, atoms, the carbon and oxygen atoms together for the carbon monoxide molecule. What's the strongest bond? I'll leave that as a mystery right now, but if you look at the bond length strength data table that's available in chapter 23, you'll find the answer to the question. But back to this. At least let's talk about where we're going. We've got the delta G0 value, so we can get delta G0R. It's this number minus twice this number. Delta G0R is minus 4.7 kilojoules. We already looked at this data point when we did this analysis earlier on. And this corresponds to a K value of 6.69 units atmospheres to the minus 1. You agree with this attached unit? What is the equilibrium constant, chemically speaking, for this thing? Well, all the reaction components are gases, so they're all included in equilibrium constant. Partial pressure of N2O4 gas up top. partial pressure of NO2 gas down below, quantity squared. So we wind up with atmospheres over atmosphere squared. That's why we get the unit of atmospheres to the -1. Again, we're reminding ourselves. If you calculate a K from thermodynamic information, you'll get no units. But if you want to do a practical analysis of the system, you may well need units. And where are you going to get the units? By looking at the equation for the reaction. Here's the equation for the reaction that always bears the units. We okay on this part? So we know, based on this K, which is a number bigger than 1, based on the fact that delta G0 is minus, this thing is thermodynamically spontaneous. But how far does it go until equilibrium is achieved? That's what we want to find out, and that's what we will proceed with tomorrow.